I think we can probably start. Thanks everyone for joining. Today we have Gustau Camps. He's going to talk about machine learning, physics, and the earth sciences. And I think I will let you start.
Thanks.
Okay.
Thanks, everyone. Let me just move this so no impact here. Okay, so yeah, today I'm gonna talk about how to live or even how to survive in this interplay between machine learning and physics, and with a special focus on earth sciences. Basically, this is the outline of the presentation. So first I will try to summarize what is the current role of machine learning in earth and climate sciences. And also we'll talk about the opportunities and challenges that we are going to face and we are already facing. This will basically bring me to the second part, which is the interesting and the meat of the presentation, which has to do with physics-aware machine learning. And I will try to summarize a bunch of things that I consider necessary, almost mandatory these days, with the data deluge and the availability of methods all over the place. These four things, I will exemplify them with a sort of with a set of case studies, and they have to do with how to encode domain knowledge, how to emulate complex codes, how to learn parameterizations, and then eventually how can we, if we can, learn causal representations from data and from simulations. And then finally, I will just come to the conclusion. Okay, so for the first part. Basically, I will try to review these opportunities and challenges of machine learning for the earth sciences. And this is our study object or subject. So we are interested in monitoring this little object of interest. We are really interested in grasping and capturing all the vital signs and the health status of the system. This is, of course, a multivariate, interconnected, complex, dynamical network system. And for that, we act as clinicians. We measure and measure and measure again and come up with hypotheses and models in order to, to characterize the system and also to be able to predict the status, right? Or forecast the status and also understand the processes undergoing. For that, we deploy all kinds of satellite sensors, but also in-situ measurements coming from different terrestrial stations, or also buoys in the sea, and also atmospheric sensors as well. And all that will help us to develop models that can actually come typically from first principles and physics, but sometimes and very often now these days we are deploying machine learning algorithms that can ingest all this wealth of information and come up with plausible predictions. So this I don't know if the video will work. Yes. So these are just a suite of products that we are able to develop these days, and you can see that we have products of characterizing atmosphere, land, water bodies, ocean of all kind. We call these cubes because you can see that they're both spatially explicit and temporally well resolved, and all together they form what we call a hypercube. And we machine learners, we love cubes, right? And we love data matrices, and so we can apply our stuff. In here, I'm focusing only on this particular product, the gross primary production, which basically accounts for how much carbon the vegetation or the canopy is uptaking. And you can see here like the seasonal cycles, and you can see details, and eventually you can exploit this information to detect changes or anomalies in the vegetation, in the vegetation and on the ground. But of course, it goes without saying that we want to exploit all the wealth of information of all the variables, if possible, all together. And we also have to recognize that these variables are interconnected, and we should kind of detect the possible connections in long-range distance connections, both in space and time. Right? In recent years, we have advocated for the use of machine learning for the earth and climate sciences. Like 5-6 years ago, we published this Nature Perspective paper, trying to promote the idea of combining deep learning and process understanding. And that was later followed by this very nice, in my opinion, very nice book, a collective effort by 80 researchers in the field trying to summarize all the advances of deep learning for earth sciences, remote sensing, climate sciences in general. So you will find there like a lot of potential applications of deep learning. This was roughly like 5-6 years ago. And we were treating problems of, change detection, anomaly detection, forecasting, explainability, causality, all of that, right? And this is apparently the case. I mean, in the recent years, we have witnessed a lot of effort and a lot of successful stories. Now you have deep learning algorithms that can forecast ENSO, I mean, El Niño Southern Oscillation. You also have very nice algorithms for doing precipitation nowcasting. And recently, like 2 weeks ago or something like that, there was this very nice paper from people at DeepMind called, well, the algorithm is a graph neural network called GraphCast. And the interesting thing is that by harvesting reanalysis data, they are able to outperform in some of the metrics of global weather forecasting as it was done until today, right? So apparently everything solves, right? But the thing is that we in Earth and climate sciences, we are not only worried about the what and the forecasting the what, but about the when, the why, and the how questions, right? So actually what we are at now these days is at these early stages. So we are able to predict and forecast and eventually detect anomalies and strange behaviors. But we still have to characterize and we still have to explain these extreme events. We also, in the earth sciences, we are very, very much interested in understanding the processes. And also, at some point, it will be really, really difficult to convince physicists that a big black neural network is useful if it is not really consistent with domain knowledge, or it is not consistent with the laws of physics, or the, like Mars or energy conservation, for example. At the same time, we want these models to be, in a way, they should be invariant, that they should be causal. And of course, we have still to tackle the big challenge, which is the attribution of causes of change and anomalies, right? And this is happening with the, with the urgent problem that it's above our heads on climate change and its impacts, and that we are all witnessing, right? So this brings me to this field called physics-aware machine learning. Probably you have seen it in many different flavors. Maybe you have read physics guided or physics informed or domain or science guided. There is like a bunch of families of methods that live inside this niche of machine learning. The truth is that when I first attended a conference, a geoscience conference, like almost 10 years ago, this was what I saw. Models without data fantasy, data without models are chaos, or kind of chaos, right? Just promoting the idea. I mean, this is the standard feeling in the climate sciences. We need data, and at the same time, we need models to understand better what are the processes, right? And this was particularly our aim there in that paper, right? So we wanted to promote this combination of deep learning, but also process understanding, and we were promoting different ways of doing this. And actually, the agenda is pretty simple. We wanted to foster the adoption of different methodologies for 4 main problems. The first one is, can we actually incorporate domain knowledge in machine learning? And if so, how can we do this? Then we also are facing the problem of, running very complicated, very complex models, climate models, or subcomponents of climate models, or radiative transfer models, as we will see in a second. And they are very costly. They are mostly based on the laws of physics, and they are incorporating all the potential subtleties. And most of them, they are based on ODEs or PDEs that are very costly to run, or at least they cannot run for longer periods. So we want to emulate it. We want to create surrogate models that can run fast. It is not only for the sake of speed up, but also because we want to generate plausible simulations as much as possible, so we can create much more ensembles of models, right? At the same time, all these models, they have some particular caveats. They come with some prescriptions of the parameters. I mean, the parameters are, of course, tuned to what the scientists at that time, well, they found it reasonable. Sometimes they're empirically or semi-empirically tuned, but maybe there's this important aspect of learning these parameterizations from data, and that could really help in having like rigid complex codes to more flexible complex codes that are parameterized from data, and that can be adaptive to different situations in space and time. And then, of course, the problem of learning representations. No, we are now witnessing this interest in large language models and large foundation models that can, in principle, extract reasonable and useful representations. In physics and, of course, in earth and climate sciences, we want to extract like useful representations. And for doing what in particular? Well, in order to tackle the big challenge. The big challenge is essentially reduce uncertainty of the projections. Here you have these two plots on the bottom. One is about the projections of temperature anomalies and under two different scenarios. On the left, you will see that these very big uncertainty bars at the end of the century is mainly caused by poor parameterizations of clouds. This is probably the biggest problem in the parameterization of climate models. And on the right, you have a similar plot, but for carbon uptake. And it is important to notice that different models in these spaghetti plots are giving you even different signs, positive and negative signs. So what is this mess? We have to constrain this uncertainty propagation. And this is an urgent matter, because otherwise we cannot really predict the intensity and the impacts that we'll have in this non-stationary scenario of climate change. Okay, let me just go now box by box and exemplifying one or two examples for each one of them, so you can see like entry points of machine learning in order to address all these little challenges that eventually can bring to tackle the big challenge. No? Let's go for the first one, encoding domain knowledge. And basically, people have been looking at two standard ways, right? So most of the times you can either play around with the loss function, or you can play around with the architecture of your model, right? So for the first one, it's a very simple but illustrative problem. In this case, the authors wanted to estimate temperature at different depths in lakes across the US. And they basically engineered a new regularizer that it was taking into account the relationship between the temperature, that it is your target variable, and the density, because it is well known, I mean, this is high school physics, that there is this relationship between density and temperature, and you should obtain like very smooth predictions of the temperature as long as you go deeper and deeper in lakes, right? So you just basically engineer this omega in such a way that enforces or tries to minimize all the sum of all the possible violations of that physical law. This is a very simple example of constraint optimization. What it was nice in that paper is that even though that the accuracy was not superb and they did not improve like very much, what they did really observe is like kind of a transportability through all the different lakes in the US. So you could run, let's say, leave one lake out across validation, let's say, and then the model still perform very, very well. While if you do not include these constraints of physics, you are actually not performing very well in those situations. Essentially, the intuition behind this is that by incorporating this kind of physics constraints, you are enforcing some sort of invariance, right, to different space or time conditions. We took that idea, and at that time we were really working on a completely different field in machine learning called algorithmic fairness. And from fairness, there is a subfield in there that you're interested in incorporating another regularizer. For example, trying to be independent or dependent to a protected variable like gender or race, for example, right? And we saw this connection, right? It is pretty much the same. You want to be dependent to a particular physical quantity, or maybe you want to be independent to another one, right? So we incorporated this function I, and for that we just took the independence measure from HSIC, so the Hilbert-Schmidt independence criterion. And then if you put that and together with a kernel ridge regression, you end up with a very nice closed form solution with clear interpretation of what is going on. And actually, you can derive as well the probabilistic interpretation with Gaussian processes, which is very nice as well because of the nice properties. Okay, a very simple toy example for that. So we incorporated this. We used this FAIR GP. And in this FAIR GP, our target was to predict the temperature anomalies in the last century. And our only input is time. And at the same time, we want to assess how much important it is to be consistent or dependent with natural or anthropogenic forcings. By natural, solar irradiance, for example, by anthropogenic, greenhouse gas emissions, land use change, all this kind of variables, right? So we develop a different GP for the same task while being dependent or independent to these variables, right? So you have kind of a Pareto front for each one of these GPs, essentially constraining the space of accuracy in the x-axis, or MSE, and in the y-axis, the consistency to that physical variable, right? Or that forcing. And actually, you want to summarize all these Pareto fronts, and we took the simpler, the better way, right? So we just basically computed the area under the Pareto front, and then you end up with a ranking of features that tells you more or less which is the trade-off, right, between accuracy and consistency. And actually, what you can really see very clearly is that both aerosol and greenhouse gases, they are basically the most contributing factors. So meaning that you cannot be accurate without being respectful or being dependent to those variables. Okay, so that's just a simple example to demonstrate that these methods can incorporate some constraints in the loss function. But actually, the game changer thing in these years, in this community in particular, was this proposal of hybrid neural networks or hybrid models. At that time, we were proposing this structure on the left. Well, basically, it's just a regular neural network, but in the last layer, we incorporate a physics-based neural network, most of the time it's coming from ODEs or PDEs. And at that time, when we published the paper, there appeared these famous, or unfamous, it depends on who you talk to, physics-informed neural networks. But pretty much it's the same idea. So you basically incorporate all the ODEs or PDEs that you want to solve into as a kind of a new layer in the optimization of a neural network. The big difference between these architectures and the architectures that were proposed in the 1994, 1995, that we have found very, very similar ideas, is that at that time you had to optimize the two coupled systems one after the other. You could not train them end to end as we are able to do now, right? Just as an example, recently we have this example of creating a hybrid model for the global hydrological cycle. Do not feel overwhelmed by the figure. It's very simple. In the box A here on the bottom left, you say basically that you're ingesting all kind of forcings for doing the hydrological cycle prediction. Basically precipitation, earth temperature, and radiation. These are time series, and then you create time embeddings. Then you fed it into a funky neural network. Most of the times are LSTMs or Camps-Valls STMs, all these kind of things. But the interesting and the distinct part here is that the neural network is not supposed to speed out the total runoff or the evaporation, which is your final target. But what it is intended to be trained is to speed out some scalars, some important scalars for an hydrological model. And these scalars, these intermediate steps are important and very, very uncertain in the community. So these are the interesting part, because when you feed your very simple hydrological model with these scalars, then very simple model that's basically a bucket model. So snowing, evaporation out, runoff out, all these kind of compensations and balance equations, then you will end up spitting out the total runoff and evaporation. But then you can train everything to end, right? So you can learn the parameters of the neural network, and then you can learn these scalars, these parameterizations, are learned from the data themselves. The accuracy was quite okay. There was the authors also observed this kind of transportability issue, and at the same time they were able to, to follow the to estimate these scalars or these parameters of the models in reasonable terms. I mean, the ranges of the values were reasonable. At least they were kind of accepted by the community, so they made some sense, right? So this is a kind of a new way to tackle the ONAL problem. At the same time, you gain something. You gain some knowledge. You gain some parameter ranges about about an old model like this one, an hydrological model. But there is like an urgent need to advance, which is the detection, characterization, and explanation of extreme events. And this is happening all around, right? So in this case, you can see a very simple algorithm to detect heat waves, to detect temperature anomalies in 2010. And actually it's basically based looking at all the amount of data in the last decade. And essentially the algorithm found something strange happened around June, July, August. And actually this has to do with the 2010 famous Russian heat wave that caused a lot of casualties and many harvest losses, etc. Right? So this is one of the objectives. Okay, we can monitor our land processes, for example, with machine learning, detect them, and eventually extract some parameters, right? Like the perimeter, the area affected, all these kind of descriptors. But at the same time, you want to attribute a cause to this, right? And this is one of the things that we are still struggling, right? For tackling this problem, we came up with a hybrid model. Again, do not get overwhelmed by the figure. It's very simple. It's essentially two branch encoder decoder. So on the top, we have like an encoder decoder in our network that it is basically ingesting all potential essential climate variables that we want to use. Imagine temperature, moisture, precipitation, GPP, all these variables, describing the system. And then you do the same thing on the bottom branch, but with models that are basically coming, they are bringing like a new perspective to the same problem. And these are basically based on indices of heat wave, indices of drought, indices that are basically handcrafted and tuned. But the advantage is that they are very nicely handcrafted and tuned from ancillary variables and for longer periods, right? So we wanted to exploit all these different views of the problem. And then what we did is to create like a three loss function to minimize. One was, of course, the reconstruction error, as in a regular autoencoder. Then was we have like a contrastive function. And then we have this scale function that basically tries to blend or match the two latent representations of both the data-driven and the models-driven, right? By tuning them, actually, you can really get very, very good results. And slightly better in general than others, I mean, that both branches independently or individually. But the most interesting part is that, again, we observe, again, this transportability issue, right? So, or advantage, no? So you can train on Russian area, let's say, and then the algorithm can capture well the physics and can be transported to other regions where we observe like other heat waves and droughts. Actually, this is a very challenging problem because even if we have tons and tons of pixels and observations, we don't have that many heat waves and drought examples after several years, right? So this is a very challenging problem where you have to impose like strong priors on the detection of the drought. But then we went further and we wanted to analyze what the network have learned. And basically we applied here a standard explainable AI technique. So it can tell you which are the most important variables and when, right? So what you can see here in this funky map is all these variables were used in the architecture. And here what you can see really is that the model is paying a lot of attention around June, July, where the drought occurs, to basically air temperature and vapor. So the fraction of photosynthetic radiation activity, right? But at the same time, these are positively correlated with the drought or the heat wave. But at the same time, you have here like, negatively correlated soil moisture deficit, basically surface moisture, root moisture. So these variables were kind of anticipating this drought, like roughly 5-6 months ahead, right? So this is important. I mean, explainability, not for the sake of explainability, but because they can help you to monitor or anticipate some drought events or heat waves that were unusual, just looking at, for example, temperature, right? And just for a simple or very short time window, for example, right? So, okay, so far so good. We know more or less what the community is doing with playing around with the laws, playing around with the architectures, right? For doing hybrid models. Another important problem we are facing is that the whole community trusts, and they do well, they trust complex codes, complex radiative transfer models, complex climate models, climate earth system models as well, right? This is the field of forward and inverse modeling, and as we all know, I will just focus on a particular problem that we are facing in remote sensing. In remote sensing, we typically rely on radiative transfer models that basically take all parameters and they can spit out like observational data, or let's say radiances. No, this would be our, let's say, causes, and these would be our effects, what we actually observe, right? And here we have like these two problems. Either we want to accelerate these radiative transfer models because they are very costly, or maybe we are interested in inverting back, right? So we get like a satellite observation, and then we want to estimate variables. We want to estimate parameters. This is a very simple comparison that we did some years ago with the standard radiative transfer models. And essentially, we try like all kind of regular machine learning algorithms, but now these days, I think its Gaussian processes are are widely used in this community, not only because of these let's say good capabilities to emulate, but also because in most of the times you don't really need like huge lookup tables to simulate with these RTMs. And GPs are kind of okay when you're dealing with 100,000 points, 10,000 points, things like that. They are very, very amenable. They can work well. And when you look at the sensitivity analysis, the GPs are performing very well. I mean, it is really difficult to differentiate what is the ground truth ranking of features with different models. And the GP is performing, yeah, decently well. Inaccuracy is better than kernel root regression neural networks, regular interpolators, etc. And then what you can do is, once that you have all these things trained, this GP trained, you can start simulating. You can start simulate radiances with whatever combination of parameters that you want, right? And you can pass in this particular problem from 20-something seconds to milliseconds, right? And this is like a big gain. So also you have the advantage, right, of uncertainty quantification in GPs, and this was quite new at the time that we proposed this. No? But still, in this setting, you still have to run your model and generate input-output pairs, and then from there you will do either the forward or the inverse with GPs, right? So we came up with a way of optimizing emulators with GPs in such a way that this lookup table is constructed iteratively. We call this IGAP, which is basically a simple combination of GP interpolation with an acquisition function, the same way that people in Bayesian optimization or active learning, they are proposing. So essentially, you run a limited amount of simulations, your affordable budget, and then you run your GP interpolator. And from that GP interpolator, you can derive two things. You can derive a diversity criterion, let's say, basically the predictive variance, the uncertainty estimate, and a geometric criterion, which comes in closed form solution, and it is essentially your accounting for how wiggly is your function, right? So we basically want to account for these two aspects of the decision function, and we combine them in an acquisition function that will tell you where to sample more, right? What you should consider to simulate more or run more simulations with your RTM. This is done iteratively, and then what we observe like very nice gains. And the good thing is that at the end of the process, you learn the lookup table, you learn your model, your emulator model, and at the same time, you learn where to sample, right? You learn interesting parts of the input space that you were not really observing that much in the previous example of just, brute force generation of lookup tables, because you just, run gridded search or whatever, or maybe let in a high-acute sampling or things like that, but not really fundamental for a particular problem at hand, right? Okay, so I also told you about learning parameterizations. And in learning parameterizations, you are basically want to play around with the RTM and machine learning. And in this case, I have to remind you that an RTM is basically a deterministic model, mapping these parameters or causes to effects or radiances, right? And in the formulation, we adopted a very simple one. Basically, we assume a Gaussian prior for the causes and parameters with a mean and a covariance. And the problem here is that the likelihood is really hard to integrate with this complex code inside the Gaussian mean, right? It's a nonlinear, hardly differentiable. It's a complicated conditional here. So we follow this standard work on variational inference by Kimman and Welling, and we just basically introduce the variational posterior into the log marginal likelihood. We choose the variational posterior to be Gaussian again, and then the mean and the covariance were estimated with a neural network. And then, yeah, it's really easy to compute the expected value of the log likelihood. Well, the thing is that this is an unusual way of performing variational autoencoders, no? Because we are actually enforcing a deterministic decoder, which is coming from the RTM, but at the same time, we have to play a bit with the noise variance in the likelihood, and we put it very low, just reflecting the fact that we are trusting the forward pass, right? So what we observed was, of course, orders of magnitude faster than regular, Monte Carlo sampling or ABC. But we also observed problems with multimodal distributions. And I bring in this here to Cambridge because I know that you have been working on similar problems, and I would like to get your opinion about this and if we can actually resolve these matters. The cool thing of this little monster is that you can not only provide point-wise estimates, which are okay, but also you can provide like the covariance matrix for the estimations, and this is of great advantage to parameterize these costly models. We run it on land processes or land parameters, and these were the first estimation of canopy water content, chlorophyll, and dry matter components from data and models all together, right? And okay, there are some issues, as you can see here, for example, in edges and in bimodal distributions, but still, I mean, it's performing reasonably well. Okay, and then that brings me to the last point that I want to make, which is learning representations. As I told you before, and you saw in that nice video, we are dealing with spatial temporal gridded data. And we are observing all kinds of changes in the global surface, right? And these changes are eventually due to atmospheric processes impacting land in distant regions and in distant times. So this is what we call in climate teleconnections, or in TV, they call it the butterfly effect, right? So something that happened in the Southern Pacific around the let's say, El Nino region is actually impacting the temperature or precipitation or greenness of vegetation in different and distant parts of the world at distant times. So what we try to do here is to use a method or to develop a method for extracting these causal feature representations. Our interest was basically looking at ENSO as the main driver. Of course, one can take a look at many different climate indices. This is just one. And we wanted to see if we can find a latent representation that it is kind of causal or grain chip causal with ENSO, trying to assess the impact of ENSO in particular space and time locations, right? So this is the architecture. It's again based on autoencoders, and it's a very simple one. We take basically a cube of greenness in Africa in particular. This is our study region, and we just learn to reconstruct it. And of course, I'm not that strict in the use of causality here. We are just incorporating a Granger causal index, right? So we are just basically ensuring that or trying to force that the latent representation should be causal with ENSO. Okay, so you can of course design this Granger causality index that is basically playing around with the latent representation and the ENSO index, which is a time series, and then you are just forcing this as an extra regularizer here with the beta parameter. I cannot see it anyway. So you can no anyway. So you can see here the beta parameter is basically putting more or less effort on the Granger causal relationship between the representation and ENSO. And actually, this is an example of what is actually happening. On the left, no Granger penalization at all, and you can see that ENSO is in black, and the blues and the red ones are basically the different latents that you are obtaining. And the red one is actually the most lag correlated latent with ENSO. It's hard to believe, but this is the case. And actually, what it happens is that it's essentially the fourth one, right? Fine. Just by incorporating a little bit of Granger penalization, we end up with that one, right? On the right, which is the red, and it is strongly correlated, lag correlated with ENSO. And actually, it happens that it pops up as the first one, which is very good because it's essentially concentrating all the variances, all the variants of the latents correlated with ENSO as high as possible. Right? But then we still struggle with the problem of, so what? So how can we interpret these latent representations? How can we say anything about what the encoder or the coder are doing? So again, we basically use the explainable AI here, a technique called integrated neuron integrated gradients. That it is basically taken locally at the gradients of the decision function of the encoder. And we apply it on this Granger autoencoder, and then what you can see here in the bottom row, you see 0 Granger penalization. Up, you see little amounts of Granger penalization, and you can really see that it is our method is actually, detecting like a lot of activity, a lot of impacts, right, in Africa in 2015, much more than the others, and this is good because what it is reported in the literature is that a lot of canopy, a lot of biomes that were affected in Africa because of an intensification of ENSO the years before. But it is true at the same time that this is like incurring in a lot of false alarms, like many different activations, too many activations actually. And actually we started discussing about the plausibility of this or that. And in reality, if I have to be honest, it's a very difficult monster to domesticate. I mean, this beta parameter, just by little bit, just by moving it a little bit, just impacts vastly on the impacts that you're basically observing here. So that's why we said, okay, let's take a little step back and let's go linear. Okay, let's go linear with that. No fancy autoencoders, but just let's go with linear algebra. And we designed this Granger PCA. And the Granger PCA is very nice because in the end, it's just like, it only involves an extra rotation, an extra orthogonal transformation of standard PCA, and actually it returns as the first principal component, well, the regular linear combination of the input data for which Y is most Granger causal. And this was very nice to see, also to apply. You don't have to train for longer times. This just goes in closed form solution. And actually the people is actually accepting it, like, as a very convenient tool. We at least, just for just a joke, one of our colleagues in working more on climate, he was saying Twitter, one-liner to do PCA plus Granger causality, right? I'm hooked. I'm fine. Yes, I love it. No, actually, people is I've seen some applications not only Earth and climate, but also in related fields like in neuroscience or in social networks, where you have similar problems of both extracting components and at the same time doing causality with that, right? Afterwards, no, if you can do it in just one shot, that's fantastic. So that brings me to the end of the talk, and I hope I convince you that we are still far away from learning what we have to learn on Earth and climate sciences. We have many challenges ahead, even though that there are like outstanding contributions these days on forecasting weather and predicting weather. Time horizons are like reduced quite a bit, and but still there are many challenges like learning these representation parameterizations, also ensure consistency. Sometimes you don't know why the method or the model is actually working, or if it is not respecting mass or energy, that's hard to swallow. And yeah, and I would say that basically these two take-home messages, right? So learning representations of parameterization from data and understand the processes is one of the things that we should kind of be fostering in this arena of Earth and climate sciences and the interplay with machine learning. I would like finally to thank a lot of people, and in particular to your brother as well, because we have been collaborating with this Autoncada for parameterization, and many fantastic colleagues and people working in different aspects I summarized in this talk. Thanks very much.
Thank you. We can have now time for some questions. If anyone in Zoom wants to ask anything, please feel free to write in the chat your questions. And maybe I can start with some general question for you, Gustau. We have seen that now there is this tendency in machine learning to use bigger and bigger models. And it seems that now these bigger models are also being applied in this area.
I don't know where I am. I cannot see the Zoom now. Sorry.
I think you are showing the background.
Yeah, but I don't know.
I think in Zoom.
So
in Zoom
here,
still seeing your slides.
Ah, okay.
There's the.
Anyway.
It might be this with this projector. Just.
Oops. Anyway.
I think in the Zoom presentation they can see that slide.
Okay.
I think it's on this on the screen. Yeah.
Okay.
Yeah. So my question is more about these big models that people are using now more and more, and it seems that there's this tendency in climate and modeling that they are also using these models. And I don't know. I was interested in your opinion on if you think that's maybe the direction to go, to use bigger models with bigger amounts of data, trying to learn jointly, or focus more maybe on a specific maybe smaller scale problems with less amounts of data, and maybe more smaller models.
Well, it depends on the task, right? I mean, you have to observe, and we have observed this tendency to create bigger models, but not only in the Earth and climate sciences, in all aspects of where machine learning enters, right? And this is, for me, it's fine. I mean, it's perfect. But I think that we should also be very cautious, right? Because of the garbage in, garbage out. I mean, of course, you can ingest all kind of data. These models, not all of them, but most of them, they have been trained with reanalysis data, which are fine. But I guess that there will be a limit on the accuracy that you can actually achieve with this. No, because I mean, this reanalysis data is basically, a summarization of both observational data, but also simulations of the last years, right? But they are kind of massaged data with a strong autocorrelation functions, etc. Right? So it's expected that you can achieve it. Like more and more data, you will basically smash the results. But At the same time, I'm more concerned about standard dictums like being right for the wrong reasons, right? And this is not even, I'm not sure if they're contemplated this, let's say, consistency with domain knowledge in these models at all. I don't know if they conserve mass or energy, or they're invariant, or what they are actually doing or saying, right? These are important aspects. Probably you could, of course, take a look at that problem as a kind of a sanity check. Let's say, let's try explainability on these models. Let's see what aspects of the data regime they are looking at. Or again, you could enforce all these constraints in order to force them to look at let's say, a subspace of the solution space, right? Which, of course, in little examples that I've shown here, we have observed like a tendency. If you do things right and you incorporate proper knowledge, domain knowledge, and sort of prior knowledge, let's say, you observe this very nice invariance capability. Also, there is something that I did not mention, is that by incorporating these constraints, let's say the nuanced part of the neural networks, they tend to be a little bit more sparser, so simpler, so faster, right? So basically, the intuition is under that is that basically you're forcing the model, the big model, to focus only on the subspace of solutions which are plausible, right? Or at least according to the domain knowledge. No? So there's a lot of things to gain by incorporating this sort of domain knowledge in the models. No? Not only for explainability, but also because of of the trust in the model, no? Because you don't want a funky model that performs well, but there's no explanation for the what or for the why, right? So yeah, but that, of course, that will depend on the application itself. No, I mean, in remote sensing, most of the times you're fine just by looking at a particular region, just getting some sample data from that region, and then extrapolating, especially upscaling these products to smaller regions, and not doing anything global. No, in weather, of course, and climate, there are different scales, both in space and time, right? So yeah, it will depend on the vast amount of data, and also your target problem. No? And there are like two initiatives that are very related to your question. One is the digital twins. In digital twins, there is like this dream, let's call it dream, by the European Commission on building like digital twins of the Earth, right? And that, of course, that will imply managing vast amount of data, but not only climate or weather data. We are talking about social, economic data, all kind of data and observations, which are very sparse. And how do you ingest all this and make sense of it? That's a bigger challenge even, no? And then I think that the thing of the digital twins, together with the big challenge of how to constrain projections on climate, it's a completely different business and a completely different story to what is happening these days with weather, which is fantastic for me. I mean, it's brilliant what they have done with GraphCast in particular, but with many other models. And the advances are brutal, actually. Very, very interesting. Yes.
Yeah,
yes.
I have a couple of questions. One, the parameterization work is the goal for those parameterizations that be used in other models like climate simulators or weather simulators, and if so, it wasn't clear from that you pushed the evaluation into the situation where you're actually using those parameterizations as part of a full global model, and how would that work? And could you use the uncertainty? How would the uncertainty be used?
Yeah, good point. I mean, this was just for a particular reality transfer model for remote sensing applications. And yeah, we validated with what we have. I mean, the RTM was a vegetation model, very, very standard in the field. It's called ProSail, and it's actually, to be honest, very cheap to run. So in principle, you could generate as many samples as you want, and then you can run whatever neural network to invert it back, and that's it. No? But it was more a proof of concept. So we wanted to run this model to get parameterizations from the RTM, which is uncertain. No? And then, of course, we validated. We validated with in situ measurements in a terrestrial campaign. Again, limited in space and limited in time, and there's a long run to a long path to run to get into climate model parameterizations. Yeah, we haven't done it yet. There, no? Some colleagues in the ERC consortium, they are doing these parameterizations, in particular for cloud parameterization, which of course there are other sort of models, not RTMs, but climate models and components. Yeah. But there's a huge interest in the climate community to do this learning parameterizations from data and subcomponents of models. Yeah. Then the other thing that you pointed out is about how to couple this, no? How to couple different models in a single one, and then how the uncertainty estimates propagate through the whole chain, no? And that's a completely crazy story, no? Because for example, in our ERC, we are only going to tackle land and atmosphere modules, but we forget about the oceans, right? Okay, we are not experts in ocean, but what I want to say is that when you start combining these subcomponents, just by a little bit perturbation in one of these subcomponents of the model, then that will affect others, right? And you don't in eventually crazy ways, because you have learned this parameterization from data and you don't really know if these are plausible or not, right? So yeah, the uncertainty propagation is going to be like an outstanding problem. Yeah.
The second question I had, so one worry I have around both building and physical constraints and interpretability is that the big models will often do inference as well as emulation. So if you're training observational data or like a reanalysis product, then they are trying to, because it will benefit the predictions for the observations or the observational constraint product, they'll try to infer the missing data, which might be like what's going on within a grid cell or the state of the sort of the ocean oscillation, and that will cause in the structure of the model there to be acausal global connections that violate the fastest known dynamics. Maybe we this kind of stuff. So in a way, you don't want to rule that out. But that makes interpretability really, really hard because the system's doing inference as well as emulation of physics. So I was wondering whether there are particular avenues to building in physics and interpretation that don't rule out or mitigate the ability of the system to do sort of inference and missing data.
That's a good point. I'm not aware of particular methods. I mean, we have been working, for example, on training models that use the same explainability metrics as regularizers. So you're forcing the model after training to be self-explanatory, right? But this is a different thing. I mean, this is So I don't know. I should think more carefully.
It's a challenging problem.
Yes, it is. Yes.
Good. I think we're out of time. Thanks everyone for joining, and see you soon. Bye. Bye. Bye.